Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on computer communications and networks. In this video, we will finish the medium access control sublayer chapter or the MAC sublayer chapter. Specifically, in the previous three videos, we have been talking about multiple access protocols, protocols that avoid collisions in a broadcast network. So we talked about Aloha, we talked about CSMA or carrier sense multiple access, we talked about MACA or the multiple access with collision avoidance protocol, which is used specifically in wireless LANs. Now, in this part of the chapter, in this video, we would like to talk about some example networks that use some of these multiple access techniques that we covered in the previous videos. For example, we talked about CSMA, carrier sense multiple access, which works as follows. If a station has something to send, sense the channel, try to detect if there is an ongoing transmission. If the channel is sensed idle, the station can transmit the frame. If the channel is detected or sensed busy, the station does not send the frame. And if a collision happens after all, the station waits for random time and then tries again by sensing the channel. That's how carrier sense multiple access or CSMA works. As a matter of fact, CSMA is part of the Ethernet standard. Now, one of the most famous Ethernet standards is called IEEE 802.3, which defines all the details related to Ethernet. Ethernet itself is a standard for building and designing local area networks, LANs using cable. So it's a standard for wired LANs. And again, the details are covered by the IEEE 802.3 standards, including the carrier sense multiple access protocol. So now, since Ethernet is one of the example networks that use CSMA, we would like to talk a little bit about it to give you a little bit more details about the Ethernet. Why do we say Ethernet revisited? Because you could check the introduction chapter and you will find that we talked about Ethernet before. We mentioned something about Ethernet, and here we would like to say a little bit more. So the classic Ethernet looked as you see here in this figure. So the classic Ethernet, the first Ethernet that was developed in the 1970s, contained a coaxial cable here, a coaxial cable, which was a common cable accessed by all computers or all stations in the network. So all computers are connected to the same cable. It's a coaxial cable that is called the ether, and that's where the name Ethernet is coming from. All stations are connected to the same cable, to the ether, using a transceiver, using transceivers. A transceiver is a transmitter and receiver pair, and this allows the computer or station to send and receive frames. Since the cable is common, if any computer transmits, that transmission is detected or successfully received by all other stations connected to the cable or connected to the Ethernet. Also, if two stations send at the same time, we get a collision and both transmissions will not be successful. That's why stations connected to a classic Ethernet need to apply the carrier sense multiple access protocol. If I want to transmit, sense the channel first. If I can detect an ongoing transmission, I will not send the frame. If I can detect that the channel is idle, I can send the frame. So this is an example network, the classic Ethernet that uses carrier sense multiple access. A little bit technical details about classic Ethernet. That cable can be up to 2.5 kilometers long with repeaters every 500 meters. So every 500 meter segment, we have a repeater that strengthens the signal and forwards to the next cable segment and so on. In total, we could have up to 256 machines connected to the Ethernet cable. And also originally the transmission rate, the data rate, was 2.94 megabits per second. In 1978, three companies, DEC, Intel, and Xerox, standardized a 10 megabit per second Ethernet. So the Ethernet became faster. It can support 10 megabits per second. Nowadays, we have 100 megabits per second Ethernet and 1 gigabit per second Ethernet, or even 10 gigabit per second Ethernet. Having said that, Ethernets as occur today don't look like this anymore. We're not using the common cable. However, we're using other devices, switches or hubs. Even hubs are a little outdated. More we use switches nowadays. So the switch is basically the way for building Ethernet and Ethernets are called switched Ethernet. So as opposed to the classic Ethernet in which all machines are connected to a common cable using transceivers, in switched Ethernets we are having a switch. So what is a switch? It's a device that has ports. As you see, these rectangles here, these squares represent ports. A cable can be connected to a port, and then the other side of the cable is connected to a computer. So if another port is having another cable and then followed by another computer, it means that these two computers are connected through the switch. The hub is the same. It looks the same. It also has ports like this, and cables can connect different devices. However, the hub works a little bit differently from the switch, and that's why in the following part of the lecture, we would like to distinguish between hubs and switches, even repeaters and routers. These are the names of the networking devices that we hear about all the time. So I think this is the best location in the course in which we can really talk to you about the differences between these devices. Before we go there, let me remind you that these cables here connected to a switch or connected to a hub are twisted pair cables, so similar to the telephone cables as opposed to coaxial cables that we used in classic Ethernets. Now, switches or hubs, what is the difference between these devices? Let me generalize more. Different devices operate at different layers. Do you still remember the layers that we talked about in the introduction? The physical layer, the data link layer, the network layer, the transport layer. Some devices work at the physical layer, like repeaters and hubs. Some devices work at the data link layer, like switches and bridges. Some devices work at the network layer, like routers. So that's the main difference between these devices. Basically, what is the layer they operate at? However, you may ask me a question. What does it mean to operate at the physical layer or at the data link layer? It means exactly the following. It means what is the actual header that this device is using to forward a message. What is the header that this device is using to forward a message? Let's recall the frame structure, the general frame structure. Let me start by the user data here. So this is the data that the user wants to send, and this data is coming from the application. So the application layer on top of the protocol stack generates some data or a message that needs to be transmitted. So this part of the frame here is coming from the application itself. So it could be the email itself, or it could be part of the email in case our email was really large and it needed to be divided into smaller pieces. So this is the user data. Now, when the application layer generates data or a message to be sent, as we know from the introduction, the application layer is not responsible for the actual transmission. So what happens is that this user data will be given to the layer below, to the transport layer, which will add a header here. So this header that you see called TCP header is actually a transport layer header. More specifically, if the transport layer is using TCP, the transport control protocol, and we talked about that briefly in the introduction, it is one of two protocols that could be used at the transport layer, TCP or UDP. If we're having TCP operating at the transport layer, you could be using a TCP header here. If we generalize, this header is always a transport layer header. Now the unit that results, which contains a transport layer header together with the user data, will be given to the layer below, which is called the network layer, and the network layer is adding its own header. So what you see here is supposed to be the network layer header. Now the whole shaded part here, the shaded data unit, is called the packet. And this is the data unit, which is handled and understood by the network layer. It contains a header called the packet header or a network layer header, followed by a payload. But that payload contains the header that comes from the layer on top, in addition to the actual user data or the message that comes from the application. Now this packet is constructed at the network layer. The network layer is still not the layer responsible for the actual physical transmission of the ones and the zeros. That's why the packet will be given to the layer below, which is the data link layer. What does the data link layer do? It will add a header and a trailer so that the whole thing is known as the frame. So this header is also known as the data link layer header, and this is the data link layer trailer. Usually, in practice, the trailer contains the check bits. Do you still remember the cyclic redundancy check? The check bits, specifically 32 check bits that are used by the cyclic redundancy check technique, and this is also part of the Ethernet standard. And the frame header or the data link layer header contains extra control information such as the address of the sender and the address of the receiver. So bottom line, what you see here is a frame. The frame was constructed by the data link layer, and now the data link layer gives the physical layer this frame. Please send this frame for me. So the physical layer will be sending the ones and the zeros that correspond to this frame. When these ones and zeros arrive at the destination machine, the destination will be able to reconstruct the frame. So as you notice, the frame contains a data link layer header. It contains a network layer header. In other words, it contains a layer 2 header, a layer 2 header, and the layer 3 header, and the layer 4 header. Now these different networking devices, depending on which layer they check, we basically organize them in such a way, and we call the repeater and the hub physical layer device, we call the bridge and the switch a data link layer device, and we call the router a network layer device. Let's try to explain this more. The switch is a device which uses the data link layer header to make the forwarding decision. So if a switch receives a frame, it is the switch's job to look at this header here, the frame header or the data link layer header, which contains something called the MAC address. So this frame header or a data link layer header contains something called the MAC address of the sender and the MAC address of the receiver. And by checking the MAC address of the receiver, the switch will decide where to forward this frame. The bridge is similar to the switch, but we will come to that in a couple of slides. The router, if it receives a frame, it will check this header here. So the router's job is to investigate or examine the network layer header or the layer 3 header. That header, the network layer header or the layer 3 header, does not contain the MAC address of the source and the MAC address of the destination. However, it contains the IP address of the source and the IP address of the destination. In the future chapter, we will talk more about the IP address. However, in short now, let's stick to the fact that the layer 2 header or the data link layer header contains a MAC address, and the network layer header or the layer 3 header contains an IP address. Now these devices look at different headers. Switches, again, as we mentioned, switches look at the data link layer header, looking for the MAC address so that they decide where to forward the frame. Routers look at the network layer header, look at the packet header itself. They will look for the destination IP address, not the MAC address, to decide where to send or where to forward the packet. Now, what about physical layer devices, repeaters and hubs? What layer do they look at? In fact, a physical layer device does not look at any header. So a physical layer device is a networking device that does not look at any header. It just forwards the data it gets. Now let's talk a little bit more specifically. This is in general the difference between these different devices. So repeaters and hubs are called physical layer devices because they just do forwarding without looking at any header, without checking any address. Bridges and switches are called data link layer devices because they examine the frame header or the data link layer header or the layer 2 header, looking for a MAC address so that they decide where to forward the frame. Routers are called network layer devices or layer 3 devices because routers examine a network layer address, a layer 3 address, looking for an IP address so that they can decide where to forward the packet, and so on. Now let's talk a little bit about each one of these devices in a little bit more detail. So what is a repeater? A repeater is a device that connects two cable segments. This is a cable segment. This is another cable segment. So any signal appearing at one side of the cable will be amplified by the repeater and then forwarded to the other cable segment so that we have an extended cable. That's pretty much it. So repeaters are analog devices. They don't understand headers at all. They don't check any address. Whatever signal appears at one port of the repeater from one cable segment will be amplified and forwarded to the other port so that these two segments get connected and basically form an extended cable. This is the repeater. What about a hub? A hub is similar to the repeater, but it connects more cable segments. That's the bottom line. So the hub is having ports, similar to what you see here. A hub is having ports, and to each port we can connect a cable. The other side of the cable is connected to a computer, as you see. So we have computers A, B, C, D, and E, F, G, H, all connected to a hub. How does the hub operate? How does the hub operate? If station A wants to send a frame to station H, for example, that frame will go to the hub. The hub, because it's a physical layer device, it will not check any address. It will not care whether this frame is going to H or G or anyone else. How the hub operates is basically it sends copies of the frame it receives along all outgoing lines. So if a frame is coming from A, the hub will forward this frame to all other outgoing lines. So the frame will automatically be forwarded to B, C, D, and E, F, G, and H. Of course, from the address, H will accept it, and the other frames will just reject it. Bottom line, the hub is a physical layer device as well. It can connect different devices through cables, and the way the hub operates is that if it receives a frame, it will forward to all other devices. It will basically make copies of that frame and forward along all other outgoing lines so that this frame is forwarded to everyone. Now, if you think a little bit, you can basically imagine that the hub has exactly the same effect as a common cable. If we have a classic Ethernet with a common cable, if we have two devices sending at the same time, we get a collision. Here as well, if we're using a hub, if A and B are sending frames at the same time, these frames will go to the hub at the same time and we will get a collision. That's why stations that are connected to each other via a hub have to apply also carrier sense multiple access, check if they can receive something first, sense the channel, and if the channel is idle, they can start sending the frame. So this is the hub. Since if any two stations connected to the hub, if they send at the same time, we get a collision, we say that the whole hub here, the hub with all connected machines here, defines a single collision domain. So a collision domain defines the set of devices that cannot be sending at the same time. So the hub, together with all devices connected to it, define a single collision domain. They cannot be sending at the same time. What is the switch? What is the switch? Again, the switch looks like that. It has ports, and each port can have a cable connected to it, and the other side of the cable can be connected to a computer, so we can have something like that. So this is a switch, and the ports are connected to cables. The other side of the cables are connected to computers, so we have computers A, B, C, D, E, F, G, H connected to a switch this time. So switch looks like a hub. Even that diagram is the same. However, the switch operates differently. How did we define a switch? We said a switch is a data link layer device because it checks the frame header to make a forwarding decision. So bottom line, the switch contains some intelligence. The hub is not intelligent. If it gets a frame, it forwards to everyone, but the switch has intelligence. So if A would like to send to B, imagine A would like to send a frame to B. Where does this frame go? It would go to the switch. What does the switch do? The switch will check the header of the frame. It will check the data link layer header of the frame, searching for the destination MAC address, and then based on this, it will know, okay, the destination is supposed to be B. It will forward to B alone. If A is sending to H, the switch will forward to H alone by examining the data link layer or by examining the frame header. That's how a switch operates. Basically, the bridge is exactly the same as the switch. It operates exactly in the same way that I used to describe the switch. But historically, if the switch is used to connect LANs or LAN segments as opposed to individual machines, we call the switch a bridge as well. So here, as you notice, this bridge is not connecting devices A and B. No, it is connecting the top LAN here. On top, you have a LAN. indicated by a common cable to which stations A, B, C, and D are connected, and the bottom LAN also consists of a common cable to which E, F, G, and H are connected, and that switch, I say again switch, that switch is connecting the top LAN with the bottom LAN, creating an extended LAN, and we will talk more about this in the rest of the slides. However, if that switch here is used to connect LAN segments as opposed to individual machines, historically the switch can also be called a bridge. Now, what else can we say about Ethernet? We can talk about the details of the frame structure. Instead of talking in general like this, the frame contains a header and a trailer, and the header contains control information like the address of the source, the address of the destination. Let's dig in here and look at the details of the frame header. This is basically two example frame headers, two example Ethernet frame headers. The first example A here is the frame header that is called the DIX frame. It's a Ethernet technology developed by DEC, Intel, and Xerox, three companies that developed an Ethernet standard called DIX. It's a little bit older. However, nowadays we have the IEEE 802.3 standard, and the frame header that belongs to the IEEE 802.3 standard is shown in B here. So both frame structures are very similar, and let's talk about the DIX frame structure first. So what you see here in the middle of the data, so this is the actual data that comes from the layer on top. Okay, so this data here contains the packet. So the whole packet that comes from layer 3, from the network layer, this is what we call data here in the context of the frame. According to Ethernet, that data is allowed to be anything from 0 to 1,500 bytes. So more than 1,500 bytes is not allowed. Now, so what you see to the left of the data or payload, what you see to the left is the header. So this is the header of the frame. And what you see to the right is the trailer here. So as you notice, the header starts with a preamble. By the way, this is the length of each one of these fields in bytes. So the preamble is 8 bytes long. 8 bytes means 8 times 8 bits or 64 bits. What is the preamble? The preamble is just a transition ones and zeros. So 10, 10, 10, 8 bytes long, 64-bit long, 1010. Why does every frame start with this? So that the destination or the receiver is able to detect the clock, to extract the clock. So basically detect the bit durations, what is the duration of each bit, so that basically it can detect the rest of the frame correctly and the bits don't mix up. Right? So this is the purpose of the preamble. And then the next field, 6 bytes long, 6 times 8 is 48 bits. So 48 bits or 6 bytes long destination address. Here in this field, we put the MAC address of the destination. And in this field, also similar length, 6 bytes or 48 bits, we put the MAC address of the source. So what is the MAC address? The MAC address is an address that belongs to the Ethernet card. So if you have a computer, it has an Ethernet card to which you connect a cable. So the manufacturer of the Ethernet card assigns an address to it, a globally unique address that cannot be used by any other Ethernet card, and this is the address that is known as the MAC address. So what you see here is the MAC address of the destination, so the MAC address of the destination Ethernet card, and what you see here is the MAC address of the source Ethernet card. Followed, we have 2 bytes that basically indicate the type, and what we put here in this type is what is the protocol that this frame will go at the next layer. So the frame here, the frame header, is processed by the data link layer, and once the data link layer finishes processing this header, the header will be removed, and then the remaining packet will be given to the layer on top, which is simply the network layer. Now, in case the network layer has different protocols operating like IP, the Internet Protocol, or some other protocols, we need to specify what is the network layer protocol that will receive the packet, right? That will receive the packet. So this is indicated in this field, which is called type. Finally, in the trailer, we have a checksum, the check bits, 4 bytes. 4 times 8 is 32 bits. So here we have 32 check bits, which are used by the cyclic redundancy check error detection mechanism. So these are the check bits. And here we have something called pad. The purpose of this pad, anything between 0 and 46 bytes. The purpose of this pad is to make sure that the whole frame is at least 64 bytes long. Is at least 64 bytes long. In the previous video, if you remember, we talked about collision detection. Carrier sense multiple access with collision detection. If a station starts sending a frame, it will not stop sensing the channel. It will continue sensing the channel during the transmission of the frame, so that if a collision is detected in the middle of the frame, I don't have to finish off the frame transmission. I stop in the middle of the frame. I can even send the jamming signal to inform everyone connected to the network that there is an ongoing transmission, so that they don't have to basically sense the channel or start transmitting. So this would improve the overall performance of the system or the performance of the network. And we mentioned in the previous video that for this collision detection option to work, successfully, the frame cannot be too short. So check the previous video. We talked about a lower limit on the frame. Now, what happens if the frame is too short because we don't have enough data here? Simply, we add pads, some dummy bits that don't mean anything. They're not part of the data or anything, just to make sure that the frame is long enough. So as you noticed, the minimum length for any frame such that collision detection can operate successfully is 64 bytes. So this finishes the frame structure of the DIX frame. Again, we have a header containing a preamble, destination MAC address, source MAC address, and type, followed by the payload, the actual data. To be more specific, that data part here contains the packet that comes from the layer on top. And now we have the trailer, which contains mainly a checksum and a pad, so that we just make sure that the frame has a minimum length of 64 bytes. Now the 802.3, IEEE 802.3 frame structure is very similar. So as you notice, we have the destination MAC address and the source MAC address, also 6 bytes. It's exactly the same. The data part, also anywhere between 0 and 1,500 bytes, is the same. The pad is exactly the same idea. The checksum here, or the check bits, the 32 CRC, cyclic redundancy check bits, are also exactly the same. However, we just have a small difference here. So the preamble, which is 8 bytes long, ends with something called start of frame. That start of frame part is 1 byte long. So the preamble itself here is 7 bytes, and the start of frame is 1 byte, which is a special, it's a special byte structure. It's a special bit sequence, which is 8 bits long, that indicates that the preamble is finished, and what comes next is the actual frame. Okay, so this is the purpose of having that start of frame. In addition to this, here in this field, in the IEEE 802.3 standard, we put here how long the frame is. What is the purpose of indicating the length of the frame? Simply because not all frames are of the same length. Look at this data part. It's of variable length. It can be anything between 0 and 1,500 bytes. So depending on how many data bytes we have, we just add the rest of the frame, header and trailer, and then we indicate the total length here in this field. Now, what does this indicate? As you notice, the DIX frame does not have a length field. And I would like to let you know, since we don't have a length field here, it means that in DIX, we have to use the start flag and the end flag, so that we basically mark the start and the end of the frame. So specifically in DIX, we must use the start and end flags. However, in IEEE 802.3, we can also use basically the length method. So in every frame, we just indicate how long it is. So once the total length has finished, it is obviously the end of the frame, and whatever comes next is the start of the frame. So this basically finishes the frame structure. The last part of this lecture is known as bridges and LAN switching. It's an interesting topic because you will notice that this switch or bridge here is actually able to learn something. That's why we call them learning bridges. So what is the deal with the bridge here? First of all, what is the purpose of having a bridge? The bridge is a switch, basically, and we know that the switch, whenever it receives a frame, it will check the MAC address of the destination to decide where to forward. However, historically, if the switch is used to connect LAN segments as opposed to individual computers, we call it a bridge as well, and the resulting structure is known as an extended LAN. How does this work exactly? Imagine that we have station A. As you notice, A, B, C are connected to a common cable, so this is a LAN, and stations X, Y, Z are also connected to a common cable, which is the bottom LAN. This is port number 1 of the bridge, and this is port number 2 of the bridge. Imagine that A is sending a frame. Where does this frame arrive? Automatically to B and C, because B and C are connected to the same LAN, if you will, to the same cable. So if A transmits, that transmission will be received by B and C and the bridge. So that frame will also arrive to the bridge from port number 1. If the bridge decides to forward along port number 2, that frame will travel over the bottom LAN here. So that frame will also be received by X, Y, and Z. So haven't you noticed that A is able to send a frame, and this frame can be received by B and C and also by X, Y, and Z if the bridge forwards. So we have an extended LAN, as if we have one big LAN, but it is basically consisting of 2 LAN segments that were extended by this bridge. Now the following question arises. Imagine that A wants to send to B. So A is sending a frame. We know that the frame has a header. The header contains a source address and the destination address. And if A is sending to B, it means the source address is the MAC address of A and the destination address is the MAC address of B. Now let's think about this frame. This frame is transmitted by A. It travels through this LAN. Who receives this frame? B and C, because they're connected to the same LAN, and the bridge from port 1. So question, is it really necessary that the bridge forwards the frame? The answer is no. Simply because the destination got the frame already. So the frame was received by the destination. Remember, A is sending to B. So A will send a frame, which indicates A as the source and B as the destination. When A transmits the frame, since B and C are connected to the same LAN, so B and C will receive the frame. C will just ignore it because it's not the intended receiver. B will accept it. However, at the same time, since the bridge is connected to the same LAN from port 1, it means this frame still arrives at the bridge. And the bridge does not have to forward the frame because the destination is B already and not X, Y, or Z. Now, let's ask a further question. How will the bridge decide forwarding or not forwarding? So the bridge, to be efficient, it does not have to forward if the destination is connected to the same port from which the frame came. So if a frame comes from port 1 and the bridge knows that the destination is also connected to port 1, it means the destination has received the frame already, and it does not need to forward to the other LAN. Likewise, if X is sending to Y, that frame will arrive to the bridge from port 2. Now, if the bridge knows that Y is connected to port 2 as well, which is the same port from which the frame just came, it means that the destination has the frame already and the bridge will decide not to forward. It will not have to forward through the other port to the other LAN. So bottom line, what does the bridge need to know so that it can really decide to forward or not to forward? Otherwise, the bridge will always forward, will forward all the time, which means that the bridge will operate as a hub. The hub is the device that forwards all the time, right? So to have some intelligence, the bridge needs to know, basically, it needs to be equipped with a table like this. This is called the forwarding table, or in real life, the MAC address table, because these hosts are indicated by their MAC addresses. So this is the bridge forwarding table. On the left here, in the left column, we have all the devices, all the stations, or all the machines connected to the extended LAN. And on the right, we have the port to which the machine is connected. So as you notice here in this configuration, machines A, B, and C are connected through port 1, and machines X, Y, and Z are connected through port 2. So we have A, B, and C connected through port 1, and X, Y, and Z are connected to port 2. For simplicity, let's imagine first that the bridge has this table. So the bridge knows this table already. How will it use this table? Let's try to give you an example. A is sending a frame to C. A is sending a frame to C. So the frame that travels indicates A as the source and C as the destination. Question, the same question again. Who receives the frame? Who receives the frame? Now the frame will travel through the top LAN, which means it will be automatically received by B and C because they're connected to the LAN, and the bridge from port 1. Now, what will the bridge do here? The bridge will do the following. The bridge will check the destination address. When it receives the frame, it will check the destination address. It will find that the destination is C. From the frame header itself, the bridge will find that the destination is C. And then the bridge will consult its table. It will find that C is connected to port 1, which is the same port from which the frame came physically. So it means the destination is already connected to port 1, which actually means that the destination has the frame already. In this case, the bridge will not forward. Now, let me try to give you another example. B here is sending a frame to X. B is sending a frame to X. So a frame will travel, and that frame header will contain B as the source and X as the destination. Now the same question. That frame, which is intended to come from B, I mean that frame that comes from B and intended to go to X, will be traveling through the top LAN, which means the frame is automatically received by A and C, connected to the same LAN. They have it already, right? And it will be received also by the bridge from port 1. Now, what will the bridge do? Again, the bridge will check the destination address. The bridge will check the destination address of the frame it receives. So the frame that comes in from port 1, the bridge will check the frame header, and it will check the destination MAC address. And from that, it will find out that the destination is X. Right? Now, what will it do with that before forwarding or not? Before deciding to forward or not, it will check its forwarding table. The bridge will check its forwarding table. It will find that the destination X is connected to port number 2. However, where did this frame come from? It was coming from B. So the frame was coming from port 1, the destination. From the table, the bridge realizes that it is connected to the opposite port, which means I have to forward. So when the bridge forwards this frame, the frame will travel along the second LAN, along the bottom LAN as well, which means that frame will be received by X, Y, and Z. So X, Y, and Z will all see this frame. X will receive it because it owns the destination address, and Y and Z will ignore it. So this is how the bridge operates. Whenever, to make the long story short, when the bridge receives a frame, it will check the destination address written in the frame header, and then it will check from this table to which side, to which port is this destination connected. So if the destination is connected to the same port from which this frame came to, it will not forward. If the destination is connected to the other port, to another port in general, it will forward the frame to that outgoing port. So this is how the bridge operates in case the table is known. Now, we see learning bridges in the title. Do we have to have a network manager that creates a table, that fills this table on behalf of the bridge? Actually, it's not necessary. The bridge is able to learn this table on its own. If some of you take the networks lab as well, you will see it in the lab. You will see how we configure switches and how we can check the configuration, including seeing this table here, which is called the forwarding table or the MAC address table. Again, MAC address table simply because instead of putting A, B, C, X, Y, and Z in real life, it is actually the MAC address that belongs to A and the MAC address that belongs to B, etc. Now, how does the bridge learn the table? It works as follows. The table is initially empty. The table is initially empty. So when the bridge starts, when the bridge boots, when it starts to operate, that table is initially empty. Now stations will start sending. Stations will start sending. Imagine that A is sending to B here. A is sending to B. A will send the frame. Again, as we mentioned many times, who will receive this frame? B and C automatically because they're connected to the same LAN and the bridge from port 1. What does the bridge do? It will check the destination address in the frame header, and the destination is B. Now it will check the table. Remember, the table was empty. Do I find B here? It's not in the table, so I still don't know where B is, which means I will forward anyway. So if the table does not have the destination as an entry, which means the table is either empty or even incomplete. So if the table has some entries but still not the destination I want, in that case the bridge will forward anyway. right? So how did the bridge operate if the destination is not known / not in the table yet? The bridge operates as a hub just in case. So let's go back to the same example. A is sending to B. That frame will be received by B and C because they're connected to the same LAN, and also received by the bridge because it's connected to that LAN also from port number 1. The bridge will check the destination address, which is B in this example. Check the table. B is still not in the table because initially the table is empty. So in that case, the bridge will just forward. Is this the end of the story? No, actually, there is still one thing remaining before the bridge forwards. Before the bridge forwards, the bridge will do a smart thing. The bridge will also check the source address of the frame. The bridge will check the source address of the frame. Who was sending this frame in the example we just gave you? A, right? So when that frame comes in from port 1, the bridge was checking the destination address and then checking the table to make a forwarding decision. However, before forwarding, the bridge will also check the source address. What is the source address of the frame that we have here? The source address is A. Now, where did this frame come from? Did it come from port 1 or from port 2? It came from port 1 because the frame is coming from this LAN. So what does that indicate? The bridge will understand that station A is connected to port 1. So before it forwards the frame, it will create this entry, the first entry. It will put A is connected to port 1. And the thing will continue. The story will continue. If any other station sends a frame, the sender goes always to the table. The sender goes always to the table. So imagine X in the next frame transmission. We finished the transmission from A to B. Imagine X now wants to send to A. X wants to send to A. So this frame will travel through the bottom LAN, which means automatically received by Y and Z, and the bridge also from port number 2. So the bridge will check the destination, which is Y in this case, because X is sending to Y. It will check the destination. Is Y in the table? There is only one transmission that happened, and only A is in the table. Y is not in the table. So since Y is not in the table, the bridge will forward anyway. It does not know if Y is here or there, so the bridge will forward anyway. But before forwarding, the bridge will also look at the source address in the frame header. So if frame has just arrived from here, it will look at the source address. It will find that the source is X. By doing that, the bridge will create this entry here. X is connected to port 2. So according to the examples that we have covered, if you have a transmission from A to B, followed by a transmission from X to Y, actually I wanted an example, the second example to be X is sending to A. So let me backtrack and cover this example so that you have seen 3 examples. So we have the transmission from A to B. It has happened already, and the bridge has one entry in the table. A is connected to port 1. Now, in the second transmission, X is sending to A. X is sending to A. Where is this frame going? This frame is going to Y and Z automatically, connected to the same LAN, and also to the bridge from port number 2. What does the bridge do? The bridge will check the destination address. It will find the destination address is A. It will check the table. A is connected. A is in the table. A is in the table. A is connected to port 1. Now question. The destination is connected to port 1, but the frame I just received as a bridge came from port 2. So the destination is on the opposite port, is connected to another port. Do I have to forward? Yes, the bridge will forward, but this time not because it does not know where the destination is. No, it forwards because it knows the destination is on the other side. However, before forwarding, the bridge will also check the source address of the frame it received. So a frame has just arrived from port 2. It will check the source address. It will find that the source is X. Now, this will help the bridge create the second entry here. X is connected to port number 2, and the same thing continues. So if in the future any other station wants to send to X, X is in the table already, which means that the bridge can really decide it has to forward or it does not have to forward. Once all stations have sent at least a frame, the table is complete. Now a couple of comments. Once once a table entry has been created by the bridge. So A is connected to port 1. Does this entry stay in the table forever? The answer is no. There is always a timeout period or a refresh period. So once a table entry is created, that table entry stays in a table for some time and then it is deleted from the table. Why does that happen? Just to make sure that we can capture basically situations of machines being connected to another LAN. So if A gets disconnected from this LAN and then now it is connected to port number 2, to avoid any mistakes in transmissions or mistakes in forwarding, the table entry is removed after a timeout period and then the bridge needs to learn this entry again. So this is the first comment. So since the table was initially empty and then the bridge starts learning the table entry by entry depending on who transmits, followed by who, and even in addition to the fact that once we have a table entry, it can get removed after some time. So this gives rise to the fact that at any given time, the table might not be complete, right? The table might not be complete. Initially, it is empty, and then later on, it might have some entries, but some entries are still missing. Even if it becomes complete, some entries can get deleted. So again, we go back to the state in which the table is incomplete. Is this a problem? This is the main question. That is not a problem. Completeness of the table is only an optimization. It helps the bridge decide forwarding or not. But if the table is empty or incomplete, the table forwards always, always, in any case. So if the bridge cannot find the destination in the table because it's incomplete, it will always forward. In short, the bridge operates as a hub as long as the destination is not found in the table. Finally, let's just have a look at a more practical example on how we can design networks or build networks, local area networks using switches and hubs. So imagine this is part of our campus. So this is our corridor in W9, and we have offices to the left and to the right, right? And each office here, each office computer is connected to a hub. So all these computers in the top corridor here, basically to the top of the corridor, are connected to the hub, and all computers in the offices to the bottom of the corridor are connected to a second hub, and then these two hubs are connected to a switch. That's a possible configuration or a possible network design. Was it really necessary that we use a switch and two hubs? It's not ultimately necessary. You know, the switch has a number of ports. If the number of ports of the switch is enough to cover all devices, we can connect the devices to the switch directly. But if the switch has not enough ports, imagine here we have 1, 2, 3, 4, 5, 6. We have 12 devices that need to be connected. And let's say we have a simple switch that has only 8 ports. It means it's not enough to connect each one of these machines to a distinct port. So in that case, we have to use some other devices like hubs or even other switches. So in this simple design in which we use a hub for all top machines, another hub for all bottom machines, and then the two hubs are connected to the switch. Let's, as a final example, trace a frame from one machine to the other. Imagine that this computer here, I'm sitting in this office, and I'm sending an email to my colleague in that office. Where does this frame go? Where does this frame go? Simply speaking, because I'm connected to the hub, I'm connected to the top hub through a cable, it means the frame will go to the hub. Now, how does the hub operate? The hub forwards the frame to all other devices connected to it. So from the hub, the frame will go to all top machines. The frame will go to all top machines and also to the switch from this port. From port number 1, think of this as port 1 and this as port 2 of the switch. So the frame will also go to the switch. Now the switch has intelligence. We understand how it operates, switch or bridge. It has intelligence. It can learn a forwarding table. So the switch will basically consult a table. It will try to look for that destination address. Is this destination in the table or not? If it's in the table, it will decide to forward because it's connected to the other side, to the other port. If it's not in the table, the switch will forward anyway because the destination is not known. In all circumstances, the frame will be forwarded along port number 2. It will go to the second hub, to the bottom hub. Now, what will the bottom hub do with this frame? Exactly how the hub operates, forward to everyone. So the hub will forward the frame to all bottom machines, right? So that transmission that came from this computer went through the hub forwarded to everybody, but these guys ignored the frame because they don't own the destination address. The switch decides to forward to the second hub, and the second hub forwards to everyone, so all bottom machines receive the frame as well. However, it is only this machine that will accept it because it owns that destination address. So this summarizes or finishes this chapter. Most important slide. Thank you so much. See you in the next chapter, inshallah.